Hi, I'm Owen Lockwood, and today we'll be talking about the Variational Quantum Eigensolver, specifically the requisite physics needed to understand how we do this optimization routine on quantum hardware. First, let's begin with a motivating example and what exactly our problem statement looks like. Specifically, if we have some molecule, how do we find the ground state energy? We begin by formalizing this using the time-independent Schrödinger equation, where our Hamiltonian h is acting on our wave function, which yields a specific energy, a numeric value, times our wave function. So this is clearly takes the form of an eigenvalue problem. Using this knowledge, we can then formulate it to visualize the ground state energy. Specifically, in this case, the ground state energy will be the smallest eigenvalue. So we can say that the expectation value of this Hamiltonian, which is going to be, if you measure this Hamiltonian, it's going to be one of the eigenvalues. The expectation value is therefore bounded by this ground state energy. So then this has all the makings, as you can see, of an optimization routine, where we want to approximate this value, which is unknown, by minimizing this value, which is the expectation value of the Hamiltonian. So we can do this by parametrizing this wave function, and we can formalize this by saying we want to find the minimum value of these parameters theta of this expectation value of the now parametrized wave functions, where h is our Hamiltonian that describes the system or molecules that we care about. So now this is the main optimization problem that we have in the Variational Quantum Eigensolver. However, this right now doesn't seem to have any way of trivially mapping it onto a quantum computer. How do we map this Hamiltonian? How do we map these wave functions? These are the information that we need before we can actually go about implementing this on real hardware. To address that problem, let's first look at what exactly this Hamiltonian is. It describes the energy of the system, and energy is all either potential or kinetic energy. So we write this h as a sum of our kinetic energy, which you'll often see as T, and potential energy V. And that describes all energy as it's either kinetic or potential. We can just say that this energy, potential energy V, is just a function of R, where R is just the description of the position, and T we can expand in the traditional quantum mechanical way and represent this as h bar squared over 2m, where m is the mass, and multiply this by the Laplacian. Note that this is not the Hessian, as you might think in the optimization literature, but rather the Laplacian, which is the divergence of the gradient. In the case of Cartesian coordinates, this is simply the sum of second partial derivatives of each Cartesian direction. So this is a very typical expansion of the Schrödinger equation, and for this Hamiltonian, the time-independent Schrödinger equation. Now let's actually look at how we want to apply this expression to our molecules. In this case, we're going to zoom in on both the kinetic and potential energy. So when we consider the potential energy, we're going to have multiple sources. We have our electrons, neutrons, and protons. The neutrons and protons are both in the nuclei, so we'll treat that as one object, and then we'll consider the electrons separately. In this case, we're going to have a bunch of Coulombic interactions. We'll have the nuclei that don't want to be near each other because they're both positively charged. We're going to have the electron nuclei, which want to be near each other because it's negative and positive. And then we'll have the electron-electron repulsions. Because they're both negatively charged, they also do not want to be near each other. So there's three sources there of potential energy, which we can formalize by writing this as a sum of however many electrons we may have. This is general to our whatever molecule we may consider. In this case, we'll consider this is the sum over all of our electrons. We have our traditional units for this Coulombic term, 4 pi times the permittivity, and then it depends on the distance between these electrons. So obviously as you get closer, the more the electrons want to be apart from each other. And then we have a very similar format to this, which is our nuclei-nuclei repulsive terms, which we simply have the exact same formula, except now we have to consider the atomic number because that tells us how many protons there are, which is the scale of the charge effectively. And we have the same constants, 4 pi epsilon naught, and our distance dependence. And then we have our third term, and this is the attractive term, which is the electron nuclei attractions. So this is a sum over the nuclei and electrons. And once again, it'll take a very similar format here where we have just one dependence on the atomic number here, and we have our, once again, the constants and our distance. So this is the full expression of the potential energy in the case of the molecular Hamiltonian. Now let's look at the kinetic energy, which is a much simpler expression. In this case, we have simply the kinetic energy from the nuclei and the kinetic energy from the electrons. So we represent that as simply the sum over the nuclei. We have our h bar squared over 2m, where h bar is the Planck constant over 2 pi, and that's squared. M is just the mass of the nuclei. And then we have our Laplacian. And then we repeat this same thing for the electrons. And we have our h bar squared over 2me this time, because all electrons are going to have the same mass here, times our Laplacian operator. And so now this, when you sum these two terms together, you'll have the full molecular Hamiltonian. However, this is somewhat of a large equation with lots of moving parts, and we want to make some assumptions to simplify this that will enable us to more easily compute and work with this equation. Specifically, we're going to be looking at the Born-Oppenheimer approximation, which assumes that the nuclei are stationary points. This is a justified assumption because the electrons are moving many thousands of times faster than the nuclei, and so this is relative to the electrons, and nuclei are very close to stationary. What this enables us to do is simplify this, because if the nuclei are simply stationary points, we can dismiss this kinetic energy term because there's no movement there. Additionally, we have this constant now, because our nuclei-nuclei repulsion is going to be dependent only on whatever 2 points we fix them to. This can just be a constant that we can eliminate. This will go to some number, whatever that Coulombic attraction or repulsion is at that distance. So this will just go to some constant c. So we've reduced this using this approximation to purely electronic molecular Hamiltonian, where it just depends on these three terms, which vary with the electrons. With this electronic Hamiltonian established, let's take a brief detour and look at what exactly this wave function can look like. So over here, when we have this wave function, we can often represent it in the classical computing sense as what's called a Slater determinant. So we have our wave function here, which is equal to some normalizing constant here. And then we have a determinant of a matrix, where this is a matrix of the different orbitals that our electrons may be in, where this is the orbital and this is the information, including both position and spin information, because keep in mind that electrons can either be spin up or spin down, and two electrons cannot be both spin up and in the same orbital due to the Pauli exclusion principle. So then we have our full matrix that we can write out in this format, and this has the necessary properties of being antisymmetric under exchange, which is since electrons must obey that property. This is all meeting those requirements, and this is the way that you'll often see this represented in the classical computing world. And so we can often write this as simply the list of orbitals that are actually filled. So you'll see this sometimes written in this format, where it's just whichever orbitals are actually occupied. And we can now move from this formalism with this Hamiltonian and this Slater determinant to a more friendly formalism for quantum computing, which is called second quantization. This is first quantization. They represent the same physical reality, but they are simply different ways of expressing it with some convenient advantages. So we're going to move from this state representation of Slater determinants to a somewhat similar and analogous representation called occupation number formalism. So we're going to move to, if I erase our original problem statement now, we're going to show that this is now, the wave function is now no longer just the whole function space, but instead it's going to be equal to some combination of these occupation numbers, where these n's are going to be binary, either 0 or 1, and we're going to use each one of them to say whether an electron is in that state or not. This occupation number formalism is also changed in the fact that in order to operate on this, we now use fermionic creation and annihilation operators. So we have our creation and annihilation operators, which will flip both these to 0 and 1s, and depending on the other states, there can be sign changes, which I'm just ignoring right there, but these will create and destroy the fermions at these specific positions. So if we have I and J, those are the specific positions that those operators are acting on. So now with this sort of state representation done, where this will be some binary vector, which you can see is very similar to how we represent our quantum states, we can move into the conversion of this molecular electronic Hamiltonian into the world of second quantization. So what I'm going to do is just rewrite this briefly so we can reduce some of the complexity by transitioning this to atomic units. So we're able to reduce the 4 pi epsilon naught, the h bar squared over m, by just saying that's equal to 1. And so in this unit space, we're able to drop all of that, which makes for much easier writing. So we have our electronic kinetic energy. Here we just have 1/2 because we dropped that to 1. And then we have our electron-electron attraction. Sorry, electron-electron repulsion. We have our sum over ij. And we have our, in this case, it's just 1 over this, 1 over Ri minus Rj. And this is just the distance between those electrons. And then we have our electron nuclei, and this is an attractive force. So we have our sum, and in this case, once again, we're dropping the 4 pi epsilon naught. It's just going to be this atomic number over this distance. So this is our now reduced electronic Hamiltonian. Converting this into the second quantization requires some handy rules that have been developed for converting these operators. Specifically, in the case of single particle operators, we map them from this first quantized form to the second using this simple rule where we now have our operator here and our creation and annihilation operators acting on where P and Q are the, as I said over there, the occupations that they're acting on, where the dagger indicates creation, lack of dagger indicates annihilation. And so in this transition, we can now see these are simply operators, and this equation can be calculated using standard integral rules. So we can simply write this as an integral where we have our conjugate here, p wave function, and then we have our operator, which in this case is the single particle operators, which is going to be this electron kinetic energy and this electron nuclei attractive force. Even though this looks like a multi-particle term because it's a sum over two objects, remember that the nuclei are fixed in this assumption, so it only depends on this electron. So then we have our information here where we have this, we have our kinetic energy of the electrons, and we have our attractive force between the electrons and the nuclei. And this is just exactly rewriting those, summing over, pulling the sum of the electrons out. And then we have our Q wave function, and then we have our with respect to x. So we can simply do this integral, and we'll get some constant here times our operators. And this is the one of the two integrals that we need to solve. The other one is the electron repulsion integral, which is specifically just for this term. And in this case, because this depends on, it's not just a function of one electron, but a function of two electron positions, we have to use a slightly different rule, which is for operators that depend on two positions or multi-particle operators. We have this, which is simply an expansion of this, where we have not just PQ, but also RS, and then we have PQ here, our operator, RS, and then once again we have our creation and annihilation operators. So we have the creation for P and Q, so we have A, dagger, P, and Q, and then we just have the annihilation for R and S. And then this integral can be formatted in a similar way. This is the same mathematical representation, but because we have these two expressions now, not just one, we have to do a double integral. So we'll have this double integral, once again, from whatever the range is, negative infinity to infinity, and we'll have our conjugate wave functions, P and Q. Note that this is now a function of two x's, right? It's not just x as it is here, it's x1 and x2 because it's a multi-particle operator. And then we have our function that we're putting down here that we care about, which is R1, R2. I'm converting from i's and j's to 1's and 2's. And then we have our R and S. And then we integrate all of this with respect to x1 and x2. And this will yield our constant that you'll see called as HPQRS. This one yields HPQ. And when we add all of this up, we can see we're going to get the final second quantized Hamiltonian form, which looks, if I open up some space over here, this is the final form we have. We have our Hamiltonian, we have our constants that we just calculated, H, P, Q, we have our operators on P and Q, and then we have our PQRS that we also specified the electron repulsion integral right there, our operators here, there's 4 of them, 2 creation and 2 annihilation, and then something that we dropped in this whole discussion, which is a constant. Remember, the nuclei were assumed to be point. That doesn't entirely eliminate them. That just adds a constant to it, which would just add a constant to the eigenvalue as well. But we should note that when we're bringing it back in. So now we have a clear representation of the Hamiltonian in this second quantized form. And if we can figure out how to map these fermionic operators into our traditional qubit operators, it seems relatively straightforward as to how we're going to apply this on a quantum computer, because we have this state representation that is naturally fits quantum computers. So the techniques to convert these operators, there's several, specifically parity mapping, Jordan-Wigner, in addition to others. In this case, I'm just going to give you an example of the Jordan-Wigner mapping, which takes some annihilation operator, the position P, and maps it to Pauli operators using the following expression. So we have our Pauli X gate at the qubit P, we have our Y, and then we have Z to Z P minus 1. And so this is a way that you can convert these operators into our traditional Pauli expressions. There's other ways to do this. This is simply a technique that is very common in the literature. So now that we have a way to map each of these to our qubits, and we have a way to map our state to the qubit, we can see how we can actually apply our molecular Hamiltonian to get an expectation value, add our parametrized gates that are necessary for this wave function to be parametrized, and we have the final process of the variational quantum eigensolver. Get the output of this parametrized gates, apply this Hamiltonian as described by our conversion into constants calculated, and then repeat that process, minimizing those parameters. So that's all the physics requisite information for understanding a variational quantum eigensolver. I'm Owen Lockwood. Thanks for listening.